Welcome everybody to today's FDTD Go 16 Applications webinar. Today we have a tag team effort from Gail Hartfield from the Raleigh, North Carolina WFO, and also Frank Elsheimer from the WFO in Columbia, South Carolina. And they're going to look at the heavy snow event in North Carolina that occurred back in January 17th of this year. Next slide. First, we'll go over some protocol. All these are recorded, and they're made available on the Visit webpage at the URL that's shown. And also, if you're interested in speakers, we're looking for volunteers for future webinars. Much of March is filled up, but there are openings in April available. So if you're interested in leading one of these, contact either myself, Dan Bicus, or Scott Lindstrom. Next. And just to go over some protocol, we'll have about 20 minutes for our speakers. You can either send questions via the GoTo chat, or we will have a Q&A period over the phone at the end of their discussion. We'll be done within 30 minutes. And remember, please don't press hold. And also remember to mute when you're not speaking. So without further ado, I'll turn it over to Frank and Gail.
Okay, thanks, Dan. This is Gail Hartfield. I'll start things off here. First, thanks for allowing us to be here to present today. I was just staring at some of the GOES 16 imagery for the impending cyclogenesis and bombing along the coast. So it's kind of fun to see this stuff in real time, but we're going to look back a little bit at a snowstorm we had last month here. And this impacted most of our region in the Mid-Atlantic and Southeast, including South Carolina, mostly North Carolina and into Virginia. Of course, anytime there's significant snow in North Carolina, it's a big deal, and this one was a little bit unusual. It was kind of an overachiever. It did generate several more inches in the peak snow area than we had originally expected in my office. So let me give you an overview of the situation, the setup, and kind of start you off with a little bit of the Go 16 appetizer before Frank launches into the 5-course meal is really good stuff. So first we have here the band 9 or mid-level water vapor imagery, 6.9 microns, one of the 3 water bands on ABI. And this is picking up water vapor in the 400 to 500 millibar range. This extends from about 0Z to about 12Z here on the 17th. And this is as the event is revving up. And cycle through here, see the digging trough to our west. It is highly energetic, and you can kind of see toward the end here, it's becoming neutral to on its way to becoming negatively tilted, and has some potent height falls with this, and of course you can see the streak of moisture there preceding the trough, almost starting to take on a leaf characteristics there. Moving on to our next cluster of pictures here, the upper air imagery here. Look at the top left, you see the 250 millibar chart, and you can see what is a nearly 150 knot jet streak that will ultimately induce some pretty stout upper divergence over our area as the event is approaching its peak. Top right there, 500 millibar chart, 12Z the morning of the event. You see the approaching deepening low to our west, which you saw in the water vapor, which will deepen further as the day moves on, as it moves over the Western Carolinas later on in the day. Looking at the 850 millibar chart on the bottom left, you can see the colder air aloft that is poised to move into the western and central Carolinas later in the day. And finally, bottom right there, the surface, it's cold and getting colder, and surface pressures are on their downward trend there. You can kind of see the marginal wet bulbs very close to freezing, evident in the eastern half of North Carolina, and that will become important with regarding precipitation type as the event starts off. So I am going to, at this point, kick it back to Frank, who will start us off with some visible imagery of the event.
Thanks, Gail. Yeah, I'm going to go through a series of satellite images throughout the day. We'll start with a couple of simple ones, and then we'll get into some more complex looking at RGBs and explain a little bit about each of those and how they can be potentially useful during an event such as this. And as Gail mentioned, if what you learn here whets your appetite, go take a look at the live data along the system along the northeast coast today, and take a look at the different bands that we're showing you here today. And there's some really pretty spectacular images that you can see, especially in the 1-minute loop in the mesosectors that really shows some interesting features. But we'll start off here. We're just looking at the band 2, and of course, one of the main reasons we look at band 2 is because it has the best resolution of all the bands on GOES East. It's half-kilometer resolution compared to the 1 kilometer that we had prior in the visible band, so we're talking about 4 times better resolution. And the snow really starts to pick up in our area of interest, which is in the black, north-central North Carolina, in the 17Z to 20Z time frame. So here's 17Z, and I'm going to step forward here, and you can really start to see some bands of some interesting cellular activity that pop out here in the visible. These lumpy areas, there's obviously, it's banded because you have areas in between that are fairly smooth, rather indicative of super cooled water droplets, not as much vertical motion. But it sticks out pretty clearly where you can see that you're likely having the highest precipitation rate taking place at this time. So I'll finish stepping through until we get to nightfall. Now I want to talk a little bit about Channel 5, which is the snow and ice band, 1.6 micrometers. This is a still image that was taken during the day, during the event. And one of the most useful features of using this particular band is the ability to take advantage of the difference between refraction components of water and ice. So in this particular spectrum here, your liquid water clouds are on the bright side, but the ice clouds as well as snow is actually darker because the ice absorbs rather than reflects radiation at 1.61 micrometers. And you can see here, if you look closely, the storm was a storm that tracked all the way from the western Gulf up into North Carolina. You can see kind of the area of snow that was laid behind it in North Georgia, central Alabama, southern Mississippi, in the darker areas with the somewhat lighter shading on either side of it in northern Alabama and in southern Georgia. Again, similarly, you can look at the darker clouds here over North Carolina at this time with the indication that these are ice clouds that are taking place versus water droplet clouds, which are brighter. So again, we'll step through, and starting again around 17Z, one thing to keep in mind when you're looking at just this channel is you really are looking at anything that has potentially ice in it. So right now it's kind of a mix of cirrus and some of the more cellular clouds. But as we get to 18Z and 19Z, these periods when it was snowing the heaviest up here in the Raleigh-Durham area and where the greatest snowfall rates and eventually the greatest snowfall accumulation occurred, you start to get that more cellular appearance and that more banded look again to the satellite imagery. So that's giving you an idea that we've got some ice in this cloud, and it's producing some growth in the crystal area, and we're getting precipitation below it. Now, of course, because it's picking up, it could pick up any ice cloud. It could also be picking up cirrus. So one way I like to look and see if I'm looking at just cirrus or the potential for some heavier precipitation is by putting on the IR on top of it, the band 10, and alphaing everything out that's warmer than minus 30. So the only thing I'm getting color scale on from the clean IR channel is that's minus 30 and colder, assuming that the majority of that is more on the cirrus side of things. So as we step through in the afternoon, once we get to 18Z, you can notice that those really high cirrus clouds, for the most part, are gone, and what's left is a lot of clouds that are warmer than minus 30 degrees C. And so we're making an assumption that there's quite a bit of ice crystal growth going on in those clouds because we're into the more favorable temperature range for that to take place. And we'll step through here. All right, let's talk a little bit about the day-land cloud RGB. I'm going to talk about 3 different RGBs, all of which have the 1.6 micron or the ice band as a component. This one is also known as the natural color RGB that was originally developed by EUMETSAT. And it's also useful for discriminating water and ice clouds to identify high and low clouds. Your high clouds and your snow and your sea ice, which of course we're not looking at in North Carolina unless something really bizarre happens, will appear more cyan, while the low water clouds will appear a dull gray or a white. This also allows you to see the land and ocean surfaces as you might expect. It's not true color because there's still a fraction that goes on, but it gives you a pretty good idea. Here's a screenshot that was taken during the afternoon of the event. Again, the ice clouds as well as the snow cover are in cyan and the water clouds are in gray or white. So let's step through, again, keeping a look at our area of interest in north central North Carolina. As we get to the afternoon hours, to me it really nicely stands out in this particular RGB where your more cellular type clouds, which have a little more vertical motion associated with them, are also coming out in the more cyan color, and to me it stands out against the whiter background with the clouds that are more supercooled water droplets rather than have that accretion growing on. So clearly this was one way that you can identify that you were going to get these heavier bands moving through on satellite. Another RGB that we have in AWIPS is the day snow fog. This one is a little more complicated. It uses the ice band as well as the veg band. Excuse me. It also uses the solar component of band 7, of 3.9 micron. One of the things you have to remember here is that band 7 has both a reflective and a radiative component to it. So in this particular RGB, we're really trying to isolate the solar component of the 3.9, as well as, of course, the band 0.1, 0.6, and the 0.86, which will be dominated by the solar component. So one of the interpretations that you can look at, here's a kind of a rough color scale for the different things that we could see in this. Again, the deep precipitating clouds tend to be the browner, and you'll have to bear with me being colorblind, is that what color looks like to me not look like exactly what it looks like to you. And then the tan is also indication of some of the deep precipitation clouds. Then I get down more to that pinkish color where we have the thick water cloud droplets, and then the white where we have the really small droplets. So again, taking a screenshot during the afternoon of the event, you can kind of see the trailing snow that was left behind on the ground over the southeast in some of the reddish colors. Then you have some dull orange, that's especially, you can see that out over the Gulf Stream to the east of the Carolinas, and that's representing your thicker water clouds. And then the bluish is representing those low water clouds, the shallower clouds. So again, stepping through, I don't want to beat a dead horse here, but this is another way of being able to look at this. And you can see, again, in this particular RGB, because the 1.6 micron is a component, it gives you an idea of where you're potentially getting that crystal growth, and you have those ice clouds going on that could enhance your snowfall rates. Finally, the last one I'm going to look at before I turn it back over to Gail is this day cloud phase. This is fairly new. I'll call it under investigation. This is done by the Japanese Meteorological Association, and they've basically been looking at this since they had Himawari 8 a couple of years ago, so it's one of the newer RGBs. You can see in the recipe in the bottom, it involves both an IR channel, the clean IR channel, band 13 in the red, but then the visible band, the red visible band, as well as the ice band. And the schematic on the right side of the image kind of gives you an idea, based on what color you're looking at, what is it that you're seeing in this particular RGB. So your green, there's thick low-level clouds. Your blue would be thin low-level clouds, water droplets. Your red is the thin high-level clouds with ice particles, so cirrus type of things. And then, of course, the different combinations there. So let's take a look and see what this is. Here's, again, the screenshot, and you can see the trailing comet tail of where the snow fell over the deep south. And again, this is pretty unusually far south. And you can also see the higher ice clouds there in North Carolina. So we'll step through, and notice at the beginning of this loop, everything's red. That's because the 10.35, or the IR, is what's making up the red portion of this recipe. So you can see that red portion all 24 hours, whereas the green and the blue components are from those in the near IR spectrum, and so therefore you're only going to be able to see that during the daytime. So as I step through, you notice that we start losing the all red, and when we get to that clear time in the afternoon, we start to see that banding again with the yellow. It really stands out where it is that you're getting your potential ice cloud growth there. You also get some interesting features. If you look to the right, over eastern North Carolina, you see the darker red, where you still have obviously some of the high thin cirrus that's over on top of the clouds we're seeing from there. And we do have the full loops of these. If anybody downloads the presentation afterwards, loops are tough to go through on these webinars, but I do have 5-minute loops of all those that you can go grab at a later time. So now I'm going to pass it back over to Gail to talk about a couple of other products that aren't just GOES related.
Okay, thanks, Frank. Moving on to the non-GOES portion of the presentation. We're going to look at the Advected layer precipitable water. First, I want to give a shout out to Sheldon Kuffelston and Juan Meng and Dan Bikes for providing some of the zoomed-in of this version of this imagery. So basically, this allows viewing of multiple layer PW to get a better idea of the vertical moisture structure and advection pattern. Of course, you're familiar with the blended total PW, which makes use of the microwave instruments on the polar orbiting satellites, but tends to be choppy in appearance due to the different sampling times. We also have, obviously, the GOES 16 total PW, and this is obviously not microwave, so it works for clear skies only, but it does provide high temporal and horizontal resolution of 5 minutes and 10 kilometers, respectively. So this product here makes use of the microwave instruments on 7 different satellites. It's available every 3 hours on a 16-kilometer grid. Basically, all swaths are advected to a common time and average, which reduces the hard edges over the regular LPW, so it makes a smoother appearance. It does use the GFS wind forecast, but the water vapor itself is not model dependent. The winds at different levels, of course, may result in features that are not exactly lining up vertically, but of course the benefit is it can be used with clouds. So we move on to the next slide. You can see here a floor panel of the Advected layer PW product as we go through the event. Now, you can obviously see the higher PW streams, which are vertically aligned, and if you look at the source region coming right out of the Gulf, so it's obviously rather juicy. The fact these are vertically aligned, as they are, does signal high precipitation efficiencies and greater chance of heavy precip in the area that it's focused on, and it is focused on the area that saw the heaviest snow. And as the trough digs into the west, you can kind of see the moisture stream pivoting, and the pivot point is over central North Carolina. So we basically had a prolonged deep moisture advection into that area, and this all confirms all of that. And this is all available online from CIRA, so you can Google that and find this product on their page there. Our next product is the NESDIS liquid equivalent snowfall product. This also uses microwave measurements from sounders on 4 polar orbiting satellites, about a 16-kilometer resolution. Some of the advantages, it does allow detection with some greater spatial detail, so it does fill in the gaps with over the data void areas, areas with some radar blockage or overshooting, or areas with few observations. This algorithm uses multiple channels that are sensitive to different atmospheric levels in order to sample the intensity of the snowfall throughout the entire precipitating column. And does best for mesoscale and synoptic scale with moderate to heavy snowfall. Unfortunately, it does not detect very light snows, so it does pick up more of the moderate to heavy rates, and it's limited to areas where the surface temperature is greater than 6 degrees Fahrenheit. And the user does need to determine the snow-liquid ratio on his or her own because this is a liquid equivalent product. It does measure hydrometers through the column. The latency can be problematic. It does have about a 1 to 1.5 hour time lag, so that's just something to keep in mind. So moving on to the next slide here, we've got four SFR images throughout the duration of the event. Most notable is the image on the bottom left there. You start to see the heavier rates, implied rates there in the imagery. And this is close to the time that surface stations in the area started to report heavy snow in that little area there. So we're looking at about 1.5 approaching 2 inches per hour rate inferred there. And of course that's not accounting for the snow-liquid ratio conversion there. So it does add some qualitative information, augments other data sources like the GO16 surface observations, so kind of can bolster confidence in what we're seeing from these other sources. And this is available online from CICS, and some training is available on NASA Sport. Moving on. What you've been waiting for, what actually happened. We had around foot totals of snow, which is significant for this area. That'll shut things down for at least a few days. The highest totals were from about Chapel Hill northeastward through northern Durham County, kind of up along just to the northwest of I-85. Everyone did see snow in the area, although in our county morning area, although the longer duration of the near-freezing wet bulbs and just general warmer surface temperatures in the east allowed for a longer period of mixing with rain, which did reduce totals. The snow-liquid ratios in the area did vary quite a bit, of course, as they often do in this part of the country. So they were roughly 12 to 15 to 1 throughout the heaviest snow area. It was kind of tough to get a lot of great quality measurements of both liquid and good quality snowfall measurements in the same spot. But in general, that's what we came up with for a common SLR. And this is higher than climatology, but of course it does fall well within the bell curve of climatological possibilities in this part of the country. So moving on to the next slide here. This was an impactful event, more so than we thought, and we're going to be looking into this. We did have some considerable accrual of snow on trees and power lines due to a few factors. First off, there was a little bit of a brief rain-snow mix at the outset, especially in the east. And this tended to freeze as the cooler air arrived, but also served as added glue for the aggregated crystals. You can see there how much snow adhered to the trees and branches, and that did result in quite a few power outages, many more than we were anticipating. So going on to the next slide, you can see the 12Z sounding at Greensboro. And this was right at about the onset of moderate to heavy snow in the western Piedmont area. And as you can see, what we confirmed from the GO16 imagery, there was plenty of ice in the clouds, strong dynamic lift, saturation in that dendritic growth layer that we inferred from the GO16 imagery. Definitely a favorable profile for heavy snow. We had a deep, low-level, nearly isothermal layer just below freezing, right around 0 to -5, and this would obviously favor aggregation and make for big, large, sticky crystals and help accumulate the snow on the trees and other elevated surfaces. If we move on to the next slide, you can see an AMDAR sounding from near Raleigh-Durham. This is close to 12 noon. This is about the time where the heavy snow was really at its peak in that area. There's no dew point trace, but the thermal structure you can see is similar to what we saw in the 12Z Greensboro sounding. The observation you can see there at RDU about this time, it was snowing about 1 inch per hour. There is only 0.06 of an inch of liquid, so that's some pretty fluffy stuff with a high SLR at that moment. We may have had some problems with the snow sticking to the side of the gauge. It wasn't adequately measuring that, so that's something to keep in mind. But certainly in line with what we saw and what the GO16 imagery was indicating at this time. So moving on to the next slide here, it's our last one here. It's simply to show this is some 0Z later that evening. So as we started getting into the little more subsidence region, as you saw in the satellite imagery earlier, it basically shows the saturation aloft is gone in the dendritic growth region. Particularly what you saw in the band 5 snow ice band, which showed the ice-containing clouds kind of departing to the east. And the forcing for ascent was winding down, but obviously in the low levels, the cold air rushed in, and it was still fairly saturated. So it was cold enough in the remaining moist depths in the low levels for the precipitation to fall at some very light needles at that point, because the temperature through that layer is about -10. So that is it for us and for this event. I'll just say thank you. I'll just give you a good overview of some of the good GO16 tools at your disposal. And thank you for your time and attention. I'll kick it back over to Frank and Dan.
Yeah, we'll just take any questions for Gail or Frank at this time.
Hey Dan, this is Scott at Sims. I just want to caution people. If you have the band 5 and it's reflective, and you have cold enough air, you might have a supercooled cloud top and still have ice for growth in the snow growth region. So in this case, we did have a glaciated top, and there was ice crystals in the snow growth region. But we have had examples in the Midwest this winter where we had supercooled cloud tops. The band 5 was nicely reflective. The Cloud Phase product showed supercooled water. But there was snow falling, so there was ice crystals in the middle of the cloud. So remember, the satellite's just seeing the top of the cloud, not what's actually going on in the important snow growth region. That's my only comment.
Okay, any other questions or comments?
Yeah, I have one comment that Gail mentioned about the latency of the Nestis snowfall rate product. Since it is a polar orbiting product, there are some latency issues, but I think what makes up for the latency issues are the fact that the snow falling from the cloud down to the ground, which could take maybe an hour or so, kind of makes up a little bit for that latency issue. But I think the even bigger thing is that this is one of the first products that uses direct readout. And many times the product is available within 30 minutes of actual flyby by the satellite. So I think that's kind of a revolutionary idea, using polar orbiting data and putting it into a product with using direct readout to get that product to the forecaster much quicker than in the past, where you normally have to wait 2 or 3 hours to see the information.
Okay, any other questions or comments?
Oh, this is Jim Gurka. Just want to thank Gail and Frank for a very interesting presentation. It was very good. And I just have a question. Were any of the JPSS products used in real time in this event, or is that still for the future?
Unfortunately, we did not at our office.
Yeah, we still in our AWIPs. The only JPSS product we currently get here in the States is the near constant contrast. Eventually, I believe we'll be getting more, but right now that's all we have. So to investigate something like that, you have to go to find a website, and it won't automatically update unless you refresh, so it becomes more cumbersome on the forecaster than for data that we get directly into AWIPS.
Right. Okay, thank you.
Jim, I do know that at least before I retired, they were getting the Nestis snowfall rate product into the national AWIPS at WPC College Park at NCEP College Park. So I know that at least that product is getting into forecasters' hands for the national snow forecasts, and maybe there may be some selected local forecast offices that
can see the snowfall rate product in real time.
Hey, Frank and Gail, this is Dave Riddell up at Eastern Region. We got in a little late here. Actually, if you all have the Data Add-ons Manager in AWIPS, both the CIRA layer precipitable water and the NESDIS snowfall rate are coming through here. So you should be able to add them onto your systems if you have not already. So while it's not a national product, it's stuff that we're bringing in through the back door here that you guys can add to your systems at some point. Just wanted to make sure you guys were aware of that.
Yeah, I also may remind you that the snowfall rate product is an operational product that is supported 24/7 by NESDIS, and so it should be out there for for use.